All right, look, while this is getting set up, we can actually get started because these are only 50-minute sessions. So my name is Alan Bateman. I work on the JDK, worked on the JDK for a long time. So for JDK9, I'm mostly focused on getting the module system into JDK9. There's a lot of things that are actually going to happen with the module system. So this talk is really about preparing yourself for what the module system might actually mean to existing applications. So this is not a talk about JDK9 features. This is very much a talk that has the correct title, Prepare for JDK9. So before I get into the talk, what I'm actually interested in is how many people have been tracking the work? Just a quick show of hands. Who've been tracking all the features that have been going into JDK9 over the last 2 years? Okay, small number of hands. So another quick poll. How many people have downloaded the JDK9 early access builds? I see 2, 3, 4. So yesterday we did a big 3.5-hour session on Project Jigsaw and the work we're doing on modularization, and we also had only 4 hands, different 4 hands. One last quick poll before I move on is who is nervous that JDK9 may break their existing code? Oh, this is actually not too bad. Those that raised their hand is you're in the right session to hear about this topic. Those that didn't raise your hand, hopefully will create some awareness about some of the changes that are actually going on in JDK9. So we still don't have a projector, but I will move on and just give some background slides. So if you could see the picture behind me, there would be a slide that it talks about what the background to the main feature that we're working on, Project Jigsaw and JDK9. We're mostly about trying to make the Java platform and Java SE in particular to be much more flexible and scalable. This is all really about building reliable, compact configurations and deployments that we can actually use in the cloud or on small devices. It's about improving the overall security and maintainability of the platform. It's about encapsulating security-sensitive internal APIs, and you'll hear me use the term internal APIs many times in this presentation, and keeping those security-sensitive APIs internal to modules. And this is all about reducing and helping the maintainability of libraries, and this goes for the libraries as in the JDK libraries and APIs. This is also important for those that are actually developing their own libraries. There's some of what we're doing in modularization will actually enable a whole bunch of new possibilities for performance improvements over time. So it's more of an enabler for these kind of things. The other big thing about having a module system and the platform structured as modules is that it makes it much easier to construct and maintain large deployments. And this goes for both Java SE and Java EE platforms eventually. It also brings us partly down the road to escape from what is known as jar hell. We're not going to address all of this in what we're proposing for JDK9, but it'll get us quite far down the road, which is good. We still don't have slides here, but what I want to talk about is just some of the work that's going on in both the JCP and also within OpenJDK around this area, particularly around the modularity landscape. So within the JCP, there is a JSR that is led by Mark Reinhold, which is the Java Platform Module System. That is the JSR that is defining the standard module system. This is separate to... Okay. I can keep going without slides. This is separate to what will eventually be a JSR for Java SE9 itself. For every major release of the Java platform, there is a JSR created that is essentially the umbrella. It's the one that actually lists down all of the major features. It covers all of the other detailed features that are any API changes that go on within the platform. So there will be an eventual JSR for Java SE9. That will be the JSR that will standardize the module graph. And we've moved the Java platform to basically a well-formed graph of modules. This will be the JSR that will standardize that. So that's JCP. That's the JCP. One JSR for the module system, one JSR for Java SE9. Within OpenJDK, which is where we do the development and the implementation of the JDK, we have a bunch of what we call JEPs, or JDK enhancement proposals, that are underway to cover the implementation of everything around the module system. So we have a JEP which goes under the number 261 that will develop the implementation of the module system that will implement the module system that JSR 376 defines. There's also a bunch of other JEPs that are around creating the module graph itself, which is the JDK modularization JEP, which is JEP 200. We've restructured the source code and the build of the JDK so that we've taken the module graph that we've defined and we've then transformed the layout of the source code and the build so it builds the JDK as a set of modules. And that is all the work that is gone into JDK 9 via JEP 201. That's very much an inward-looking JEP. It's not interesting to those that are actually downloading and using the JDK. It's really, really important for those that are actually working on the JDK themselves because the source code is organized by module. There's another JEP that we have called 220. I have a couple of slides on this, and I hope we will get the projector running and you'll be able to see these, is that we're changing the way that the JRE and the JDK are actually structured, what they look like. There's no rt.jar, there's no tools.jar. I'll get into that later in the presentation. We also have another JEP which is about encapsulating most of the JDK internal APIs. That is a lot of what this presentation is about, so I'll cover that later on. So that's the sort of the landscape of what's going on. 2 JSRs, we've got 5 JEPs at the moment. We'll also have another JEP coming along soon for what we call the linker, because we're working on the link phase for modules, and there will be a separate JEP for that. I want to talk now, just give a few background slides just around APIs in the JDK, and also just talk a little bit about some of the policies around compatibility and how the platform actually evolves in a compatible way. Because this really goes to some of the issues that we want to get into in this presentation. When you look at the Java doc for Java C or for EE, you'll see that all of the APIs, or the majority of the APIs, are in packages like java.something, java lang, or javax.swing, or whatever they might be. These are all the standard APIs. These are the APIs that are, I think we might get things working here. So they are all defined by various JSRs within the JCP. There's also a whole bunch of other APIs that are not standard. Some of those APIs are JDK-specific APIs that are supported and documented APIs. Others are just internal to the APIs, or internal to the JDK. All of the sun.star tree of packages, they are JDK internal APIs. The com.sun tree is a mix of supported APIs and JDK internal APIs. And this has been a source of confusion for people for many, many years. If I listed you out the name of a couple of packages in com.sun, then I'm pretty sure that most people will not know whether, is that a supported API or is that part of the JDK implementation? There's always been a lot of confusion around this. So one of the wonderful things about modularizing the platform is that we have to go down through each one of these areas and find out and quickly identify, is this a supported API? Is it not a supported API? The answer to the supportedness question should be a Boolean. It can't be some gray area in the middle where, well, we don't know whether that's supported or not. Because with modules, we have to clearly identify what is supported and not supported. The main thing to understand is standard APIs, applications, libraries supposed to use them. The JDK internal APIs that are documented and supported, they're okay to be used. All the internal APIs, this is the area that where we need to spend a lot of time on, because when we bring in the modules and we bring in strong encapsulation, it means that these internal APIs will no longer be accessible. So to some extent, this is part of the compatibility story, as we will see, because there's so many libraries and applications that are actually making use of these internal APIs. So what I want to get into now needs a couple of slides. We will see whether this works. Take your questions while we're okay. We're just conscious of time. Please fire away. Okay, so the question is what about what about APIs that are deprecated, and to use your phrase, will they get kicked out? And so we've always been clear for many years is that removing random deprecated methods is more trouble than it's actually worth. It would break too many things. I have a couple of slides here where I will actually go through 6 methods that we need to eliminate and remove in JDK8, or sorry, Java C9. That will be the first time that we will ever have ever done this. We have very, very good reasons for this. So the answer to your question is no, we're not randomly removing things. Kirk has a question.
Yeah, can you address the APIs that are now commonly used that I guess which should have been considered some private, such as unsafe?
I have several slides coming up on unsafe. And in a few minutes, this technical problem will resolve itself, and we will talk about what we're doing in JEP 260. If we can't resolve this, I'll skip some of the slides that need to be shown, and I'll go straight to some of that. So I better move on here because okay, so I just want to talk just about general compatibility points, and then we will actually get to Kirk's question about what we call critical internal APIs. Okay, general compatibility policies. So those that actually attended Brian Getz's keynote this morning will have created some bit of awareness of what's involved in evolving the platform, especially from the language point of view. But we have to consider all of the compatibilities, changing behavior, libraries, everything all over the place. Everything has potential compatibility impact. The general compatibility policy, if I was to summarize it into a single line, is that if an application uses only supported APIs and works on release N, then it should work on release N+1 without any changes and without recompilation. That is the high-level sort of one-line summary of what we try to aim for compatibility. It's always been possible to remove supported APIs. Way back in I think with Java C6, they established a policy around this. We have not used this, but the policy has always been possible. It's always been possible to remove supported APIs. We just haven't done that before. Managing incompatibilities. Managing compatibilities is mostly just about judging the risk and the impact based on actual data. Those that might have attended Brian's VM Summit yesterday, you may have heard him go through all of the different iterations of different prototypes and the compatibilities that you run into at different attempts. A lot of the time what we're actually doing is trying out different things, using actual data to decide whether something is going to break existing code or not. We regularly run analysis, both static analysis and other analysis on large corpuses of code in order to understand what language features are used and what library features are used. We're going to try this. Yeah, sorry about this. So let me just continue on here without slides. The other thing we spend a lot of time is when we are making incompatible changes is there is always a lot of communication about it. There's also the fact that we do early access builds every week means that there's always builds available for people to try things out, and there's an opportunity to provide feedback. So sometimes we do actually screw up on things. We don't realize the compatibility impact on something. And based on feedback, we can make some course corrections along the way. So that's one of the good things about having the early access builds out there. Another thing, and people probably may not be aware of this, is that many times when we're making incompatible changes, we actually are forced to introduce system properties or other flags or options to get back previous behavior. all of these tend to get documented in release notes, which I'm pretty sure nobody actually reads. So everyone laughs at that, but there is for every single release, there's always a very, very detailed document produced that lists down all the possible API changes, behavioral changes, and where possible, flags to actually restore existing behavior to keep existing code actually working. I don't know whether we're dealing with a compatibility issue here or not. Okay. Okay, I'm now just going to rewind the stack a little bit because I had to skip over slides that I couldn't actually show earlier on. So this is one of the slides I actually wanted to show earlier on when I was talking about sun.star APIs. For those that brought binoculars, then you can actually see the date at the bottom of the slide says 1996. Just let me press X here to zoom back in again. Can you see this? Yep. Okay, so what it says under sun.star is that the sun.star packages are not part of the supported public Java interface. This is JDK 1.0 and 1.1 documentation. So even back 20 years ago, there was an attempt by way of documentation to communicate that the sun.star APIs were not part of the public interface. Since JDK 6, the Java C compiler has enforced this. So if you ever compile things that use the sun.star API since JDK 6, you've been getting a compiler error. Can I do a quick poll as to who here ignores compiler warnings? Yes. Shouldn't have made them so useful, according to Kirk, and this is all what we want to talk about. So I want to move on here because I've talked a few of these things here. So what this presentation about is mostly about the first item I have on the slide here. I want to talk about the implications of encapsulating the internal APIs. I also want to talk about a couple of other incompatible changes that we're doing around removing APIs, changing the binary structure, removing some features that you probably have not heard of, which is good. The version string, which has gone into JDK9 and has broken a lot of things. I want to talk a little bit about that and just create awareness of the underscore. Right, we'll start by looking at some internal APIs. So this is data that's collected that is collected from an analysis of about 100 different libraries and products. There's about 30 Oracle products in there, and the only reason we use them is for doing any static analysis is they're easy for us to get a hold of. And there's about 70 or 80 other open source libraries that we had there. What we're plotting here is the usages of internal APIs. So what we have in the y-axis here is a usage count. So there's some internal class is being used on this data set is being used. There's 125 different usages of some internal type. There's 100 and something of another type, and then you'll see the graph quickly drops, and it tails off, but it never tails off quite to zero. On this analysis of 100 different products and libraries, there's over 700 different internal classes being used. I'm just wondering, would anyone want to guess what the highest, which internal class was used the most? Okay, I heard unsafe over here. Well, interestingly, we've cooked the data here. It's actually sunMISC base64 encoder decoder. Now, on this particular data set, the highest usage was actually sunMISC base64 decoder, and sunMISC came up in second highest. If I was to go further, the third highest usage was sunMISC base64 decoder. Now, why would anyone want to use sunMISC 64 decoder, base64 encoder decoder? We have a standard API for this since Java C8. There is a Java util base64 encoder. Why did it take us so long to put a base64 encoder into the platform? I do not know. There is no reason whatsoever for anyone to ever have used it. They used it because it's there, it's convenient. It's not a critical internal API. This is an API that just people use because it was handy, it was there. So there's a huge amount of analysis being done on the internal API usage. And what has been proposed is to split these APIs into two buckets. The non-critical APIs, which is, there's two reasons that they're in this bucket. One is there's no evidence that they're actually being used outside of the JDK. They're not showing up in any static analysis. Or, like base64 encoder decoder, they're really just used for convenience. Then there is the critical APIs. So these are the internal classes, or meant to be internal classes, that would be difficult or impossible to implement outside of the JDK. Clearly, SunMISC on Safe is something that you have as a critical API. You cannot implement that outside of the JDK. So the proposal in JEP 260 is to encapsulate all the internal APIs by default. So all those are used just for convenience, and those that we know are not, or we've no evidence that they're used, they will be encapsulated. We would also encapsulate anything that has a supported replacement in 8. So if there's a standard API for something, there's no reason to use what the old internal equivalent. We cannot and are not proposing to encapsulate anything like SunMISC on Safe that is a critical internal API. The proposal is that they be deprecated and, if possible, removed in 10. I cannot guarantee that SunMISC on Safe will go away in JDK 10. There's a lot of different JEPs and a lot of good projects going on that will chip away over time a lot of the use cases that require using Unsafe today. Whether we will get there in JDK 10 to the point where it can be removed, I don't know. Finally, the proposal is that for to keep existing code working that's accessing internal APIs, there will be a command flag, and we have this in the Jigsaw builds if you try them out today, to be able to essentially break the encapsulation and get at these internal APIs just to keep existing code working. And I have some examples of that in a few minutes. As things currently stand in JEP 260, this is the list of APIs that are proposed to be critical internal APIs. SunMISC on Safe is up there. The Signal and Signal Handler class are up there. There's also some usage in SunReflect. Reflection get caller class is something that's used by a lot of libraries. Logging libraries need to be able to get the caller. We do have a stack walking API that has gone into 9. It's not providing exactly the equivalent, so this reflection get caller class is listed as a critical internal API for now. There's also reflection factory. This is what serialization libraries use to actually be able to do a lot of instantiation without going through constructors. So there's a lot of lower level libraries are hacking into reflection factory. So this is listed as a critical API for now. Now let's get back to the data set that we had a few minutes ago. And for those with the binoculars, you'll be able to read this slide. For everyone else, it's just color-coded. So what we have here is anything that is a critical API is listed in orange. Anything that's actually in purple is an internal API. It's non-critical. It will be encapsulated. This is the list of the classes that were in the previous graph, where you see SunMISC base64 encoder at the top. It's in purple because that can go away. There's a standard API. SunMISC on Safe is in orange. Is because it's a critical API, and so on. There's a whole bunch of things that are color-coded here based on the fact that there was never any need to ever use these things. There was always a standard way to do this, but for whatever reason, people were making use of them. All right, so we'll not get into the details of all that here because we've. But what I do want to do is how do you actually find usages of JDK internal APIs? Another quick poll. How many people here have tried JDEPs? 3, 4. That's kind of disappointing. It's disappointing because because this is a very, very useful tool to do static analysis on your libraries or applications to see what libraries they're using, what internal APIs they might be using. We put this into JDK-8 as part of a whole slew of other prepare for modularization work that we did in JEP 162. so that there's always a tool available for those using JDK to be able to look at their libraries. Robert Schulte from one of the Maven folks has actually written a Maven plugin for this that you can run in your build as well, and it'll actually report usages of internal APIs. So that's really, 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 really useful. So there's a whole bunch of things that JDEPs can do. I used them. Showed some of the options in the talk yesterday. The option I want to talk about here is a very simple option, which is -JDK internals. So you can give it as input a jar files, a directory with jar files, a class path of jar files, and it will do a static analysis on those jar files and print out what their dependencies are. For the example I'm using you here, I've taken one of the Glassfish libraries. I've taken its security jar file. You'll find I'll pick on Glassfish a little bit on this because they've actually been working with us and actually to fix a lot of their issues. So I've been using some of their code as examples. So what will happen when I run JDEPs on this is I'll get output like this. This is listing down all of the dependencies, what modules does it depend on, and it reports a whole bunch of internal API usage that is in this library. In this case, there's code in this Glassfish jar file that is using some security util, and it's using a whole bunch of things like X509 name. It's using a whole bunch of other security types. They've clearly cloned a security provider from the JDK and modified it for their own use. So there's a whole bunch of internal API usages here. Oh, what will happen now is if they try to run this. So this is using internal APIs. What will happen when they run this on JDK9? Because this is an internal API, modules will strongly encapsulate these internal APIs. So let's see what happens. We end up with a scary exception. I've actually got a whole slide deck on scary exceptions. And this is just one slide from that. And what we're seeing here is an illegal access error. Illegal access error it typically tells you you've got a mismatch between your compile time environment and your runtime environment. You compile something that was originally public, and you change it maybe to non-public, and then you try to run some code that hasn't been recompiled. It will fail at runtime with a legal access error. Or the core reflection equivalent or with method handles, you get a legal access exception. This is what the scary message actually is saying. It's saying that some class, Sun Enterprise Security Provider Policy Wrapper, that's one of the Glassfish security classes, is trying to access this Sun Security Provider Policy File class. That is an internal JDK internal class. It's in a module we call the Java base module. That's the core of the system. And the message goes on to say Sun Security Provider is not exported. Within the module system, packages are exported at the granularity of package. And in this case, the Sun Security Provider package is not exported. So that's just an example from Glassfish as to what will happen if you try to run this code that's accessing an internal API. Let's take another little example. This time I'll take just an example from Gradle, and what will happen is when I try to run Gradle, this compile Java task suddenly fails on me, and in red I've highlighted what the error is. Could not create an instance of type com sun tools javac API javac tool. Something's going on here. It looks like something's broken in javac. Now, Gradle, if you're familiar with it, has an option to get a stack trace. You can get to diagnose errors is usually straightforward. So we run Gradle again, this time with the dash stack trace, and the exception reveals itself. This time it's the core reflection equivalent of the illegal access error we had a few minutes ago. This time it's a legal access exception because Gradle's trying to access some internal class. So I'm picking on the G's maybe today, but Gradle have fixed up a whole bunch of issues to get Gradle to work in JDK9. So things are actually moving on there. So my point with these last couple of slides is just to show you that existing code, if it's not recompiled and you just take it, ran on 8, it's using internal APIs, you run it on JDK9 with modules and strong encapsulation, things can potentially break. We will not panic. I said in JEP 260 that we would provide a command line option to allow existing code to work. It's an ugly command line option, and this is what it looks like. The name of the option is xadd exports. The value to this is there's 3 pieces of data in the value. There's the module, that contains the package that you want exported, and then it's who you want it exported to. Now, I don't want to get into the details today about unnamed modules, but for now just assume that the token all unnamed means all, just think of it as a class path or code that's hasn't been compiled into a module. So in order to get Glassfish to run, this is the command line option I need to use. I need to list down all the internal packages that it's using, and that means existing code will continue to work. I see a few people actually writing down the option there, so just I will have some links at the end to some of the JEPs, and JEP 261 details how to break encapsulation and explains more of the format of this command line option. Also, just to say is the Glassfish folks have been working with us, so they've in their Jira they've created issues for every one of the internal APIs that they're using, and this is the issue that is that tracks this particular issue with the security policy file. There's the general format, as I said: source module, the package, target module, all unnamed is just a special token. Just think about it as class path for now. We'll move on now from encapsulating most of the internal APIs to talk about some of the other changes that breaking changes that are in 9. We are removing 6 deprecated methods. Shock horror. We're actually removing methods. We've never done this before. These are methods that we identified a long time back that were going to be a hindrance to modularizing the platform. These methods don't allow us to properly break out the core module from the rest of the system. These methods are deprecated. There's replacement methods for setting up property listeners on Java Util Log Manager. So these have been flagged for some time. We've got some good replacements for at least for the Log Manager in Java C9. And that's it. So of all the 30 or 1,000 or so methods within Java SE, the fact that our modularization only has to remove 6, that's actually a good thing. Just on the PAC 200 methods, we have yet to find anything anywhere based on even a static analysis of over 100,000 libraries. We've never found any usages of these. We're confident we're not going to break too much by removing those. Changing the binary structure of the JDK. So far, this has been the biggest hit on the tools in the ecosystem because the binary structure is, even though it's not an API, is something that the tools have always relied on. So what is the motivation here for changing the binary structure? So the current binary structure, and I'll show it in the next slide, is something that came about in JDK 1.2. There's a JRE, there's a JDK. A JRE is inside a JDK. We want to move away from this structure. We want to move to a much more efficient, module-oriented format. If I was presenting today about the linker, I would show how to create custom runtimes that have your own modules and JDK modules, and trying to fit those into the legacy layout is very problematic. So let me just first show you what we have in the JDK today. We have a JRE that you will recognize. There's a bin directory in there. There's a lib directory. That is where rt.jar lives. It's one of the most well-known jar files. rt.jar, people will recognize it. The JDK then creates sits around that and adds another bin directory and adds another lib directory. Embarrassingly, we have actually copies of some of the tools in both bin directories. If you look in the JDK, you'll actually say, oh, there's a Java there and there's a Java there. Which one should I use? We have jar files up in the lib directory of the JDK, and we have it down in the JRE. This is a little bit kind of a strange format, but it's the way it has been since 1.2. The other thing is we're using jar files, which is based on the zip format, which is 30 years old, is a really, really inefficient way of actually storing classes and resources for the JDK. We can do so much better with other formats. So we want to move away finally from the zip format. One final thing we want to do is sort out the confusion that there has been for many, many years as to what's configurable in the JDK, what's not configurable. When you look in the lib directory today, you'll find security policy files, you'll find font configuration files, a whole bunch of other configuration files. Which of them can I edit and configure without breaking the system? That's always been a confusing point. So this is what we're moving to. It's a very, very simple structure, which we call the modular runtime image. This is what JEP 220 is all about. We've eliminated the GRE within the JDK. There's only one bin directory. There's only one location for the tools. All user editable configuration is moved into the one location. There is no jar files in the JDK anymore. There is a lib directory where we have a completely new container format that's highly optimized for class loading that sits inside that. We want to be able to evolve that over time as we add in a whole bunch of optimizations and other ideas. And so this is a very, very simple format. When I say that there's no jar files in the JDK, it's really, really important that you understand that I'm only talking about what's inside the JDK runtime image. Jar files are not going away. We're not changing the way people deploy applications or anything like that. You can still run with jar files. And we've even enhanced jar files with modular jars, as I was talking about in the Jigsaw presentations yesterday. The important thing is that jar files are disappearing from within the JDK image. This has an impact on tools, IDEs, and a bunch of other things that are used to accessing what's inside of the runtime image. So we knew this would be a big issue. So this is one of the reasons it went into JDK9 early. It's been in the JDK9 build since the end of 2014. In addition to having it into the JDK9 builds early, we have also put in a supported API by way of a file system provider that allows tools that are running on JDK8 or running on JDK9 to be able to access the runtime image as a file system. So by using Java NIO file system provider mechanism, tools can run and use the file system provider to access a JDK9 runtime image. So that has been really, really useful. Most of the mainstream IDEs have already moved and have support for this, which is great. A couple of other features that have been removed: the endorsed standards override mechanism. If you're not an app server, you probably won't know what this is about, but it's essentially about being a way to provide upgraded versions of some of the components that are in the runtime. Java EE, SE, and E have shared a number of components like the transaction API, the common annotations, web services, JAX binding. These are things that have their own standalone technologies within the JCP, and app servers have historically had to override those. We're removing that mechanism completely as we move to modules, and we're replacing it with a much better, saner mechanism called upgradable modules. We're also removing a complete misfeature called the extension mechanism. This is something that we haven't seen any usage for 10 plus years anyway, but was very much a problematic feature. There's lots of other changes that are going on in the JDK, and in JEP 261 we've attempted to list down all of these incompatible changes. A lot of these are actually behavioral and implementation things, but they are libraries will have dependencies on them. So we've changed, for example, we've completely replaced the extension class loader, for example. It was always an implementation thing that these were of type JavaNet URL class loader. We've seen code even in Gradle that would blindly cast the system class loader to a URL class loader and assume it's a URL class loader. Now it fails with class cast exception. This is something the Gradle folks have fixed only a couple of weeks ago. We've removed the notion of the boot class path. It's essentially gone. Therefore, some of the options around that have been removed. System properties around that, like Sun boot class path, also go away. So there's a lot more. This is a big disruptive change, moving to modules. You're changing quite a lot of things under the cover. Mark Reinhold likes to say is that we're jacking up the house and we're replacing part of the foundations, which is probably a good summary as to what it means to move to a modular runtime. So check out JEP 261. It has all of the details that we know about. I'm not directly involved in the Verona or Project Verona or JEP 223 work, but I just wanted to create some awareness of it. This is all about changing the JDK version string. And I'd like to read something from the from the JEP that helps to explain the motives for why the version string is changing. So from the JEP, it reads, which release contains all of the most recent security fixes? JDK 7 update 55 or JDK 7 update 60? It looks like JDK 7 update 60 is 5 releases ahead of update 55. So therefore, it really must include more security fixes, right? That conclusion is incorrect. These 2 releases contain exactly the same security fixes. Security releases based on the previous minor releases are odd numbers, incremented by 5 or by 6 if necessary in order to keep the update number odd. It's been really, really confusing. So we're finally, after all these years, addressing the issue of the version string. But this has impact. It changes the output of Java version. It changes the system properties. It changes everything we know about the version string. And this is going to impact some code. Here's a table from the JEP, which shows the old and the new. I've only one thing to say on this slide. After 20 years, we're finally dropping the leading one. Here's the system properties, so you can actually see how this changes. So this has been in JDK 9 since the end of 2015. I remember telling Iris about that when this went in, it was like setting off an electromagnetic pulse in the atmosphere, and it took out all of the electrical equipment on the planet. There's a lot of code out there that does parsing of the version string. That is very, very sensitive. A lot more than I actually really expected. I think more than the project originally expected. So this is something to be, I'm including a couple of slides in this mostly to create awareness of this. If you own some code in there, make sure you check it out. By the way, a lot of libraries have been reacting to this over the last couple of weeks and fixing up things. It's mostly the changes to deal with the version string haven't been that hard, but you're dependent on someone else to whatever library owns it. Final thing I just want to create awareness is of the underscore. The underscore is no longer going to be allowed as a 1-character identifier in Java C9. So there's a JEP 216 called Milling Project Coin, has a number of updates to the language. This is one that has been planned for a long time. The compiler has been warning about it since 8, and that support is being dropped. My guess is you won't see too much of this, but I just wanted to create awareness of it. So finally, preparing for JDK 9. The most important thing and the biggest impact of moving to JDK 9 will be on code that's using internal APIs. So it's really important if you own libraries or you're making use of other libraries is use tools like JDEPs or other static analysis tools. I mentioned about the Maven plugin to look at the code and to identify those internal API usages. There is a get out of jail card with the exports that I showed, but this is going to have a big impact. The fact that after 20 years, you're finally putting a wall around these internal APIs. The version string, we know that has an impact. That's gone into JDK 9 already, impacting libraries. If you own code and you're not trying out the build, just at least think about what it means to deal with the new version string. Underscore, just to create an awareness of that. The big thing is if you're a tool. If you're a tool you maintain a tool, I should say. If you that is accessing the runtime image and is accessing rt.jar or is making other assumptions about the layout of it, you possibly will need to change. We have a new API in there through the file system API to allow tools to access the runtime image. So that's the way forward for that. Finally, it really is a supported API, which is good. And the other important thing is try out the early access builds. So we're currently at JDK 9 build, let's see, what is it? Well, if I use the new version string, it's JDK 9-9 plus 104. So it's when we've been doing weekly builds. So 104 means we're actually on the 2-year anniversary of weekly JDK 9 builds. So try them out. We also do almost weekly builds of JDK 9 with Project Jigsaw. So with the module system and the work that we're doing in Project Jigsaw and OpenJDK, we're pushing out early access builds every week as well. We're not yet at the point where we're bringing the module system into 9. We want to get there soon. Exactly when that isn't exactly clear yet. But when we bring that in, then you will see the real impact of encapsulation of internal APIs. So please, if you have code, try out the builds and send feedback. So more information. So I have links to Project Jigsaw, which is where we're doing the work on the module system. I also have links to the early access builds. There's a colleague of mine, Mandy Chung, maintains this page called the Java Dependency Analysis Tool. So we've been collecting data based on JDEP's usage to help those that are running JDEPs and identify usages of internal APIs. And she's kept that page up to date with where there are supported replacements for those. So you will find in that table some MISC base64 encoder decoder. Don't use that. That's an internal API. Use Java util base64 instead. And then there's the link to the JEP 223 with the version string. So that is all I have. And so I think we have a few minutes.
Yes, we do. And the slides will be up on the JDK site.
Right. Please fire away.
What are you planning to use underscore for?
What are we planning to use underscore? It does not have a planned usage yet. So this is all preparing for possible futures, but there's nothing being planned for the 9 time frame. Okay, so Kirk is asking about we're replacing the boot class path. Right, so what's happened is moving to a modular runtime, there is no notion of a boot class path anymore. Everything is just modules. We still allow for things like appending to the boot class path and agents that need to add to the boot class. They'll continue to actually work. But there is just no equivalent. We still have a boot class loader. In fact, if from the slides from yesterday I went through how class loading has not changed, visibility has not changed. So we still have a boot loader, still have extension, app loader, all of those things. We're just changing those would break too much code. There isn't a class path essentially for anything than modules. Modules aren't loaded from the class path. They're loaded from something called a module path. So the module path is the replacement. Prepending on the module path is done through upgrade modules, and there's only that will be restricted to only certain modules that can be upgraded. If you think about it, there's bootstrapping issues in there. Your system would already be up before it could actually attempt to even find core classes, so it couldn't search the module path. So Kirk says ask about masking classes for debugging purposes. So there is a low-level patching mechanism, and JEP 260 documents it. It's called xpatch, that you can actually use for ad hoc patching to any module. That's useful for testing scenarios. It's also using for ad hoc performance diagnosis. You want to try out some little thing without rebuilding the JDK, you can use the xpatch mechanism for that, and that's very useful for patching anything in any module. It's actually more powerful than what was the boot class path. Any other questions?
About unsafe. Is there any ideas of giving us the capabilities of unsafe as a normal package?
Okay, so the question is whether we're going to do anything about unsafe to make it a normal API. Okay, so unsafe will continue to be accessible in JDK 9, maybe later. There are many important efforts that are going on that will essentially make a lot of unsafe redundant. So rather than taking unsafe as it is now and just making it an exported API, these efforts are looking at the use cases where unsafe is being used today. So some of the work that Paul Sandus is doing on var handles for Java C9 renders a lot of unsafe usage redundant. There's other work that's going on in Valhalla and Project Panama in OpenJDK. Project Panama is all the native code integration. That will eliminate some of the usages of unsafe as well. There's other cases around serialization that there isn't efforts yet that will avoid usages of unsafe. But over time, I think people will chip away at the different use cases that will make unsafe close to redundant. So there is no proposal to just make unsafe or a subset of it as a public API. Instead, it's a case of working on the use cases and do the right thing so that you can access them through without going through such a low-level API.
Okay, we'll say thank you.
And apologies, things were a little bit rough there when we started without slides, but that's okay, we got through it. That's okay, that's okay. Right, thank you.